What's going on, class? Welcome to another lecture. We are still in chapter 9. Last video we talked about the method of equilibrium. We talked about stress transformation equations, and now we're going to get into Mohr's circle. You may have heard of this. Mohr's circle is another way that we can solve these types of problems, but particularly Mohr's circle, named after the guy who came up with the concept. It has to do with determining the principal stresses, which means a maximum, principal stress is a maximum normal stress a body experiences at a given angle. And also for them to be maximum normal stresses, this means that the shear stress at this particular angle is equal to 0. So tau xy is equal to 0. And so some orientation, we're talking about the different stresses that are being applied to, different types of bodies at various angles. There is an angle where there is a maximum portion of stress in the x direction and a maximum stress in the y direction, and the shear stress at that particular angle is 0. So Mohr's circle is a way that we've been given to determine these things. And so what I'm about to walk you through is how to look at some of the problems in the presentations that we had before, the previous problems, and use Mohr's circle draw Mohr's circle based on that, and actually use that to help us solve what we want to solve. And when it's all said and done, you'll be able to determine how convenient that is versus the method of equilibrium versus the stress transformation equations versus other things. So to get things going with the Mohr's circle, I believe it begins to talk about it in section 9.4. There are 4 things you need to know when you're drawing a Mohr's circle. Number 1, you need to know the center. We'll call that C. The center of Mohr's circle will always be equal to the average of the stresses and 0. So the x-coordinate is the average of the stresses. So we'll call that, and we won't call it, but we'll basically let you know that that is sigma sub x plus sigma sub y divided by 2. The average of the normal stresses is 0. That's the center. Number 2, what you need to know is the radius of the circle. The way we determine radius, we'll use the letter R, is basically this distance equation. So it's the square root of first term under the square root under the radicals sigma sub x minus sigma sub y all over 2 squared plus tau xy that you are given, and that will give you the radius. It's the distance, basically the distance formula. That's the radius. That's the second thing you need to know when you're solving for Mohr's circle. The third thing that you need to know is the range. Or basically plus or minus the radius, or how far, or how long is the diameter, even, is another way to think of it. But the range is given to you as this: the first coordinates, or the sigma 2, being the center minus the radius, right? That's going to be to the far left side, and then the center plus the radius. Quite simple, right? That is the range of your Mohr's circle. And then the last thing you need to know, number 4, is your reference point. You need a reference point. Your reference point is basically, or is usually, given to you in the problem you're attempting to solve. We'll use A to denote our reference point. And the reference point is basically your normal stress in the x direction, sigma sub x, and your shear stress, your tau sub xy. Those are the 4 things you need to know: your center, your radius, your range, and your reference point. And so what we're going to do right now, we're going to go through a couple of problems and basically draw a number of more circles. And I'm going to show you basically the process of finding those principal stresses after you have already drawn your Mohr circle. All right, so let's go with 9.45 first. 9.45. We'll set that here so that we can see it. 9-45. 9-45. This is in the back of the chapter. And basically, it just gives us problem 9-3. It's a problem that we've already done before, but it says, hey, solve this using Mohr's circle. Solve this using Mohr's circle. So the first thing we want to go ahead and do is find the values or the coordinates of those 4 items that I told you are very, very important. And then we'll use that to draw Mohr's circle. So the first thing is the center. The first thing is the center. Now, you may notice over here by looking at it that our sigma sub y is equal to 400 psi. Make sure we can always identify that. And then our sigma sub x is a negative 650 psi. Those are the values of those 2 items, those 2 stress values. And so again, starting with number 1, the center is going to be the average of these 2 and 0. So the average of these 2 are, let's see, we got negative 650 plus 400 over 2. It's the first term and 0. We can rewrite that. I'll make sure I have my trusty calculator on me as we begin to work through these things. Negative 650, of course, we can do it in our head. That's obviously put 250, but go ahead and go through the motions. Plus 400 divided by 2. So 125. 125 is the first part. And actually, it's a negative 125 because we got negative 650. So negative 125 and 0. That is the center. That is the center. Number 2, we need to get the radius. The radius is given by this equation. I'm going to go ahead and just plug the numbers in as I write it. The radius is, underneath the radical, we got sigma sub x. So a negative 650 minus 400 over 2 squared plus, now what's tau sub xy? What is tau sub xy? Well, if we look at our original diagram or original problem, there is no shear stress. So we can just put 0 here. So if I go ahead and solve for this, negative 650 by 2. Then I'm going to square that. And then it's under the radical. So the value of this radius is going to be equal to 525. That's the radius. That's R. Next, what is our range? What is our range? Our range is basically the center. The center minus the radius. So we have over here the center being negative 125 minus 525. That will give us a negative 650. Right? And 0. That is our first term. And then the second term is, it's going to be plus. So negative 125 plus 525, it's going to give us 400. Parentheses. That is our range. And then last but not least, what is our reference point? What is our reference point? Our reference point, number 4, denoted by A, is simply sigma sub x, which we know to be negative 650, and tau sub xy, which, again, according to our diagram, we do not have anything, so that's 0. Those are the 4 things we need to draw our Mohr circle. So I'm going to go ahead and pull out another sheet of paper just to make sure we have enough space to proceed in drawing our Mohr circle. Proceed in drawing our Mohr circle. So right here in the center of the page, we're going to use that as our center. We know the center is, based on what we just determined, is a negative 125 and 0. Negative 125 and 0. So if you can imagine, if this was the center and this was the number line, I need to get a straight edge so I can make sure I don't get things too crazy moving along. All right, I got this little gift card out here. So imagine there to be a x-axis, not necessarily a number line, but an x-axis over here. Since the center has an x-coordinate of negative 125, a negative 125, the y-axis is somewhere over here, right? That's 0, 0, because now we're at a negative 125. Does that make a little more sense? Hope you all can see that, and it kind of clears up a little bit. Next, what we have is a range, so we can go ahead and determine. And I'm gonna go ahead and use this mug I have here to draw our circle before I even begin to put other things in place. But we want to make sure we keep things in perspective. And you know, this is going to be a pretty small circle. Scratch the proportions, right? Yeah, I use a mug for now. All right. Hoping that dot is in the center of this mug. The only reason I'm drawing the circle first, because you got to have a nice clean circle, and I don't want to do it freehand. But it tells us our range, right? If we go back and look at our radius, I'm going to put radius on pause number 2, but let's look at our range. We have that over here on this side, it is a negative 650 and 0. Negative 650 and 0. And then here on the positive side, again, don't let the scale throw you off too much. We have a 400 and 0. Right? Those are our range numbers. Those are our range numbers. And then we have our radius, which makes perfect sense. Based on this, right, the numbers, we go from, our radius is 525, so going from a negative 125 to a negative 650 is 525. That's the distance of our radius. But then lastly, we need a reference point A. And we are told right here, just why we found out that our reference point is negative 650 and 0, which ironically just happens to be the first term of our range. So this point here also serves as our reference point, Now, what we're going to do is use this circle to define or to find our principal stresses. And our principal stresses are basically what we were already finding in previous videos, which is sigma sub x and tau sub x prime y prime. Sigma sub x prime and tau sub x prime y prime. So now we know that this is our reference point. We will basically look at our radius there being from our center point to our reference point. And we're going to rotate that line a certain number of degrees. How do we know that degrees? Well, it comes right back to our original problem. If we look at it, we see that there's a rotation taking place, a rotation of 60 degrees. 60 degrees. Now, what we're going to be doing is rotating it 2 times theta sub x, s, 2 times theta sub s. So here's what I want you to do, right? I want you to look at this and remember that if we were to just draw this triangle, we know that this is 60 degrees here. What we have done in the past is we have made our x coordinate perpendicular to that face. X coordinate is perpendicular to that face. X prime. We know that the original x axis is in this direction. And so we have to ask ourselves the question, what is this angle? What is the distance from the original x-axis? Well, if you know geometry, if you were to rotate it down 60 degrees, right, you would know that this side is 60 degrees before it gets to vertical. This is 60 degrees. All right? So that means that this particular supplemental angle is equal to 30 degrees. That is 30 degrees because that right angle is 90 degrees. So what we're doing is we're looking at this triangle. We're looking at how much of a rotation did this perpendicular x prime take from this original position as an x-axis. We found that angle to be 30. And so here on our Mohr circle, I hope you all catch this. On our Mohr circle here, we're going to be rotating from our point of reference 2 times that particular theta sub x. And so we're going to rotate this way down a full 60 degrees. This is 60 degrees, such that now the line is going to take us to the point which, guess what, happens to be our principal stresses of sigma sub x prime and tau sub s prime sub y prime. All right? And so the way that we would solve for this, I don't want you all to miss this, the way we would solve for this is simple geometry, right? So we know that this is going to create a triangle if we were to just look at that angle. And I want to use a different color here just so I don't confuse you too much, right? I'm drawing this red here just to kind of show that it creates a triangle. Just to show that it creates a triangle, right? So we know that this particular x value is going to be this distance of 125. So this is negative 125 already just to get there. And then we need to know this particular distance as well to get the x coordinate. So in order to get the x value or the sigma sub x prime, this particular equation would be as so. This is equal to negative 125. What else? Minus the 525 radius times the cosine of 60. That's the equation. Now, how will we know the y coordinate, which happens to be the same value as the tau sub x prime sub y prime? Well, we just need to know this particular, right? We just need to know this particular length. And this particular length is simply 525, the radius, times the sine of 60. Now, if we plug and chug that, and we get our answers, we will find that, and come on this side, so confuse you all. This value is a negative 387.5 psi and a 455 psi. And this is how we used Mohr's circle to solve for these stresses. So I hope that made a lot of sense to you all. Again, we kind of went the slow approach, and you'll be able to do these steps, the center, the radius, the range, the reference point. It becomes second nature to you after a while, but we're going to walk through it, continue to walk through it as we continue to draw these other more circles. After we got this particular value, we're able to identify these particular points in our Mohr circle. Once we can identify our points in our Mohr circle, we rotate it from our reference point 2 times the angle of interest, or the supplemental angle, down to the point that gave us our sigma sub x prime and our sigma or our tau sub x prime y prime, to practice our drawing of the Mohr circle, So it simply says draw Mohr circle that describes each of the following, So we're going to go through these steps to find the center, the radius, the range, the reference point, all of these, so that we can draw the respective Mohr's circle. So kicking things off, let's look at A. And I'll pull out another sheet of paper if I need to. But A, the center, is the average of these two. So 800, the center is going to be 800, boom, minus 600. I think that's where we are. 800 minus 600. Use our computer. Okay, we lost the visual for a second. Test. All right, here we go. Yeah, so my 800 minus 600 over 2, and then 0. So that tells us it's going to be 200 over 2, which is basically 100, 0. Next, we're going to get our radius. Our radius is going to be make sure I get this right. Sigma sub x, so 800 plus the 600. So we got 14 over 2. This is going to be squared. For a, we don't have a tau xy, so we're going to just do with a 0 there. That's going to be 700 squared, and then the square root. So this is going to be a range of 700. That's where we are there. A radius, I'm sorry, not a range. And then our range here, this is our range. It's basically going to be plus minus that 700. So on one hand, we'll have a range of a negative 600, 0, and the other side being a 800, 0. And then last but not least, a reference point. A reference point is just going to be our sigma sub x and a tau sub xy. All right. Reference point A is going to be 800 and 0. So I'm going to go ahead and draw this first one. This first one, I'm going to draw it on this sheet of paper, which should fit. And then we'll do the other ones on another sheet of paper. So our center point here is 100, 0. That is C. It always helps for me to go ahead and do an axis off of that center point when I'm drawing. This is where a good straight edge comes in handy. That is not the center point. So let me change that real quick. All right, I had to work that out really quick. The vertical axis is actually a little bit to the left of that because that's 100. It's still the center point, but we're gonna have to come over here to get the vertical axis. And so from there, we're gonna hopefully make that center point our center point of our circle. We'll do our best to get that in the center. Best we can. All right, draw my circle. And whenever Mohr did this, the guy who did this, he had a really steady hand. He pulled out a mug or something like this too. Oh, that's not bad. That's a nice little center point. Good stuff, good stuff. So that's our center point. So now we know our range over here on this side. We're gonna call this sigma sub 1. This is 800, 0. And then on this side, this is called sigma sub 2. By the way, this is a major and the minor. The major and the minor, major and minor. Over here, we got a negative 600. 1. All right, and then our reference point 800 is right here. That's A. And speaking of A, that is the A example of drawing more circles. So now let's do this one. Let's get out another sheet of paper and do the next one. Let's do the next one. Let's do the next one. Draw or get used to drawing as we learn this. So for the next one, we're looking at All right, gotta get another sheet of paper. So the next one we have, basically, what we're looking at is sigma sub y, sigma sub y. So it's pretty straightforward. So sigma sub y, not even x, that is equal to a -2. Sigma sub x, based on that, is 0. We don't have anything there. And sigma sub, or tau sub xy is also equal to 0. So if we were to make sure we understand our center in this case is going to be a -2 divided by 2. -2 divided by 2 is a -1 and a 0. Make sure you all getting the same thing as me. So -1 and a 0. Our range next, or our range, our reference radius. Our radius is going to be a 0 minus, or a plus 2 over 2 squared plus 0, and that is equal to a 1. Our radius is a 1. Our range should be quite easy to figure out. Our range is going to be a -2, 0 and a 0, 0. That's our range. And then our reference point, A, is just 0, 0. All right, so let's go ahead and get that center point going. Center point is -1, 0, -1, 0. I think I may be able to do this one freehand. So -1, 0 is our center point. That's C. If I were to draw a horizontal axis there, and as I said, this was the vertical axis. So the circle of it would look something like this. So that the major would be 0, 0, sigma 1. The minor is -2, 0. And yeah, the reference point is 0, 0. So this is also A. That is the B, the second one we were asked to draw. All right, move right along. Let's get this last one going. So C, and we're asked to draw the center point. Oh man, the center point is quite easy for this one. The center point for C is 0, 0. Because there's no sigma sub x and there's no sigma sub y. So the average is 0, and that average of 0 plus 0 is 0. And then R is going to turn out to be 0 squared plus 20 squared. So the radius is 20. The range is basically going to be this radius plus or minus. So we're talking about -20, 0, and a +20, 0. And then lastly, a reference point. A reference point, just to remind you, is always going to be sigma sub x and tau sub xy. This doesn't even exist. That's 0. And the other one is 20. So we're talking 0 and 20. So now let's go ahead and draw this. Let's say the center is exactly what we know it to be, 0, 0. So that means that the x and y axes are going to intersect at that point, okay? Like we're tempted to do anyway in most cases. Let's go ahead and draw that here. And the vertical axis here. There you are. So that's 0, 0. That's the center. Or use my mug this time. Yeah, how good I get it on the center. We're gonna work it out. Wow. Wow. Look at that. Look at that. Right on the money. Right on the money. So here we go. We have our minor or major over here. Sigma sub 1 being 20 plus 20 and 0. Our minor, sigma sub 2 being negative 20 and 0. Our radius is 20, which makes a lot of sense. And then our reference point is being 0, 20, 0, 20. Did I do it the right way? 0x, and reference point then being 0, so 0, and x coordinate and negative 20. So down here, this is our reference point A, 0 and 20. All right, so there are no angles involved in any of these, so we don't have to worry about rotating things here and there. But I want you to take a look at this. We just basically ran through the rehearsal, if you will, of the practice of drawing Mohr's circle. By doing A, found our center radius, range, and reference. We can sketch that out. B, only had a sigma sub y, did the exact same thing. They would sketch that out. And then we did the same thing for C. So that one right there, 9-54, should give you just a little bit more practice when it comes to drawing Mohr's circle, because that's going to come in handy. And we're going to definitely keep moving right along with another example of where the Mohr circle can help us solve what we're looking for. All right, now let's look at 9-60 right here, 9-60. It tells us to determine the principal stresses. And let me just clarify something for you, because I understand that you may have heard these terms. I said principal stresses, and I've used different terms here and there. But when they're talking about principal stresses, what they mean in this case is the major and the minor principal stress. So the sigma sub 1 and the sigma sub 2 that we have on our Mohr circle. That is, in fact, technically what our principal stresses are. And then it says B, find the maximum in-plane shear stress. So in other words, we're going to find on the Mohr circle, where is tau the maximum? Where is tau the maximum? And that's going to be pretty obvious for you when we get to that point. But now let's start things off here, looking at what we have here, this little stress cube here, where we have sigma sub y is equal to a positive 10 KSI. Sigma sub x is equal to a negative 15 KSI. And then we have tau sub x, y is equal to an 8 KSI. So there we are. And so let's go ahead and go right off the bat and find what we need to see, our center point for our Mohr circle. It's going to be the average of these two. So that's 5 divided by 2. So that is a negative 2.5. 0, that's the center point. The radius is going to be equal to, let's go ahead and write that out. A negative 15 minus a 10 squared 2 plus 8. That's going to be equal to 15. And this is square here as well. If your calculator agrees with mine, your answer in this case should be a 14.84. 14.84. That is the radius. The range is going to be plus or minus that. So the range should be able to calculate itself as a negative 17.3 0, and a positive 12.30. Now check this out, y'all. This range right here already gives us our principal stresses, because you remember how we drew the circle, and I'll draw it for you in a second, where you know the range, one range is going to put you on the right side, the other is going to put you on the left side. So this here is already our minor. Boom. And this is already our major. Boom. But let me write the last portion, which is the reference point. The reference point R, or the reference is A. That's how we denote it. A is equal to sigma sub x, which is negative 15, and tau sub xy, which is 8. All right, so let's do this here. That's going to be our center point. Center point, we've already determined to be negative 2.5, 0. Center point. I'll do my method of drawing my axis, my x-axis directly to the center point. That's at a negative 2.5. So I'm just going to shift over a little bit for our vertical axis. All right. Go ahead and draw my Mohr circle. All right. I think that's good. Boom, there we go. Not too bad, not too shabby. So our range is going to be over here. We're going to go over this way, 14, which is basically negative 2, subtract from there. And so now we're looking at a positive 12.3 and a negative of negative 17.3. Then the reference point A is going to be negative 15, so somewhere over here, and a 8. So that's going to be right about here, our reference point A. Reference point A. That's negative 15, 8. That's our reference point A. Now, again, minor and major. All right, so major is sigma sub 1 here. And this is sigma sub 2. So to answer this first part of the question, we can easily say that for A, sigma sub 1 is equal to 12.3 KSI. And sigma sub 2 is equal to negative 17.3 KSI. There you are. So that's part A. And then part B, it says the maximum in-plane shear stress. So let's get this right. Let's get this. Where is the shear stress? If this vertical axis refers to our shear, and this horizontal axis refer to our normal stress, where will we find the maximum amount of shear stress? It will be either here at the top or at the bottom. And the way most people draw the Mohr circle, and it depends on however you feel comfortable. A lot of people draw the bottom going down as positive. Some people say, okay, this is negative, and this is going to be positive. And in fact, I believe the book does so as well. So if that's the case, then basically we would want to know what is the lowest point on the circle to give us our maximum in-plane shear stress. What is this point right here? And if you look at it, really all that is the radius. All that is the radius. That's what this is. It's the radius. So this radius right here equates to what is axiom? The maximum in plane shear. The maximum in plane shear is equal to, in this case, 14.84 KSI. 18.84 KSI. So that answers the question here. But I'm not going to stop this yet because I want you all to notice something. I want you to be aware that this reference point, we didn't do too much with it, but this reference point, we're to draw a line from it to the center point, the negative 2.5 C. On this Mohr circle, we can recognize something. We know that this angle, we would know that this angle going counterclockwise back to the x-axis is going to be equivalent to 2 times theta sub p. 2 times theta sub p. And then in this direction, going the counterclockwise direction, which a lot of times we refer to that as the positive direction, then that will be 2 times theta sub x. So get this, if we wanted to determine, let's just say we want to determine theta sub p, we could look at this triangle here, right? And say that the tangent, we're using tangent because we know this component, we know that component. But the tangent of 2 theta sub p is equal to 8, right? Theta is opposite over hypotenuse, opposite over adjacent. I'm sorry, opposite over adjacent. So 8, which is down over adjacent, which is, in this case, is 15, negative 15. But the distance from negative 2.5 to negative 15 is actually 12.5. You might look at that 15 and be tempted to put 15 there, but we start off at a negative 2.5. So that distance is 12.5. So this particular equation is what we could write as a truth based on this triangle. So if we go ahead and take the inverse tangent of both sides, we took the inverse tangent of both sides, we could come out by saying 2 times sigma p is equal to the inverse tangent of 8 over 12.5. Let me get that for you real quick. .62 degrees, which since this is 2 times theta p, 1 would simply be, divide that by 2, 16.31. 16.31, that would be 1 degree. And since this is going in the clockwise direction, and I said before that it's customary that we use the counterclockwise as a positive, we can make this a negative because it's going in the clockwise direction. And so that is what we will find if we want to find the angle. And let me see. Oh, well, it's part of it anyway. Specify the orientation of each element. So this value is basically what we're able to find here. So the complementary angle would just be, so what's the complementary angle of 32.62? We subtract that from 90, or complementary angle may not be the technical term, but what completes it at 90? 57.38. So we could say that, I'm just gonna write it over here, 2 times theta s is equal to 57.38, which means that a single theta sub S divided by 2, 28.69. Boom. So those are our angles. Those are our angles simply by using trigonometry in that case. And that gives us the orientation. And so we found pretty much everything we needed to find here. Simply by going through the process of drawing our Mohr circle here, we actually already found what ended up being our maximum in-plane shear stress, which was B bar. And then it says our principal stresses, which I just shared with you, is just sigma sub 1, sigma sub 2, which was found right here, all right? I just wrote it out here just to be clear. That is what you will be putting into your answer column. And then down here, when it comes to the orientation, I was able to establish and show for you that this counterclockwise direction from our reference line would be 2 times theta sub S. If we were to go clockwise back to the x-axis, that would be 2 times theta sub P. We can use trigonometry to find out that, and as well as that, and that is what gives us our orientation. So before I let you go, obviously this may not be the method of choice, but it's necessary for you to learn as a part of this course. So I encourage you to make sure you understand all of this. However, you get into a situation where you are just looking to find the orientation, you're looking to find the maximum in-plane shear stress. There are some equations that you can plug and tug. So I want to make sure I write that for you. If you've already looked into your textbook, you may already have it down in your notes. But here's something we can always count on. If we want to know our maximum tau, in other words, our in-plane, or maximum in-plane shear, that's going to be equal to square root of sigma sub x minus sigma sub y over 2 squared plus tau xy and squared. And guess what that is? You look at it, it's basically the same equation as the radius. So the radius is our maximum in-plane shear stress. And then if we want to know our orientations, tau, or tangent rather, tangent of 2 times theta sub P is equal to tau xy over sigma sub x minus sigma sub y divided by 2. And then if we want to know the other angle, tan sub 2 times theta sub s is equal to a negative sigma sub s minus sigma sub y divided by 2 all over tau sub xy. Those are some nice equations to keep in your toolbox. Like I said, is in the textbook as well. And that is a shorter way to just go ahead and do everything we did on Mohr circle. But again, it is necessary. It's part of the curriculum for you to understand how to go through Mohr circle for this particular class. I hope you were able to follow along with all of the methods we talked about, the equilibrium method, stress transformation equations, the Mohr circle in this particular lecture, as well as these equations which help you determine the orientation as well as the maximum in-plane shear stress. Hope you all got that. Go back and freeze, rewind, do what you need to do to make sure you understand the concepts, and all the best to your future assignments.